Ruh-roh. Also, how about the piece of paper that I also gave you at the beginning of class? Have that out. Not yet, though. I mean, we're not going to do it just yet. All right. Last section of chapter 4. So before we even get into that, obviously, we're just going to just bypass the lab, unfortunately, which kind of leaves a void for next week. So I will be doing some adjusting of the schedule for next week, even though you probably haven't looked at it yet. But if you have, I will be making some minor adjustments. What those are yet? I got an idea, but I'm not 100% certain about it yet. So you'll see. Just get on Google Classroom every day. Check my plan book. I would check my plan book daily because I do make changes on that often. Okay, even if it's just small, like I might take something away or add something to a certain date. Just get in the habit over the next couple of weeks of doing that. You know the routine by now. Okay. So in section 4, we were talking about everyday forces. Now we're going to be finishing this off tomorrow, but I'm not. You're going to have like a 2 or 3 question, I think 2 question homework assignment. Okay. I don't spend a whole lot of time or ask a whole lot of questions regarding the stuff in tomorrow's discussion. That's why your homework's going to be very short. But it is somewhat of an interesting concept, but your book doesn't really go into a whole lot of detail with it. So anyway, everyday forces. In this section, we're going to explain the difference between mass and weight. I think you probably already know that. Find the direction and magnitude of normal forces. What is normal force? Force perpendicular to the surface of the object is on. It also counteracts what other force? Gravity, typically. Okay. We're going to describe air resistance as a form of friction. That's at the very end of tomorrow. And use coefficients of friction to calculate frictional force. So we're going to be doing that last bullet point today as well as tomorrow. So mass and weight. Okay. Before even reading this, what is the difference between mass and weight? Exactly. Mass is basically what you are, all the matter that you are, okay? Your weight is determined off of your location. And that location is going to be determined, or is going to determine what your gravitational acceleration is going to be. That's really what the difference between mass and weight is. So it's a vector quantity, and the magnitude of the force is going to be a scalar quantity. Okay, it's called weight. To calculate weight at any location, yes.
I have a question.
Uh-huh.
So if I went and stood on top of a tall mountain,
Uh-huh.
with a scale, and weighed myself,
Uh-huh.
and I stood at the bottom of
Mariana?
Without
Not marinara, I know that.
I thought marinara. But weighed myself. What is the difference in the gravity of
Well, there are, I should say are, because there's multiple. There are arguments that based off if you are in a certain location on Earth, well, you'd obviously have to have all the water removed from the Marianas Trench, okay? Because you wouldn't survive anyway. But there are arguments and statements that say if you are at extreme altitude changes, that it could be adjusted slightly, or if you are at a different location in terms of like the poles, that it could be, but you are still essentially on the same body planet. So gravity, in terms of its force, is going to be very small in terms of its fluctuations. It's more so if you were to go to a different celestial body. Okay, it's like the moon, planets, stuff like that. So good question. Good question. Because, like I said, there are some statements for that being true. So to calculate weight at any location, it simply goes back to Newton again. Force equals m times a, but this time the a is gravity. Okay, so you don't necessarily have to put that on there, but if you want to, you can. But now when you start talking about normal force, okay, this is where you want to start putting down some formulas here. Anyway, again, as we stated earlier, the normal force acts on a surface in a direction that is perpendicular to the surface itself. As you see from this image here, that square, that box that is on that platform that is elevated to an angle. The force of gravity goes straight down again from the center of the box. However, the normal force is got a slight angle to that, to that gravitational force, because that force, that normal force, is set up so it's perpendicular to that angled platform. And then you see where theta is located. Okay, it's the deflection essentially from the perpendicular of what it would be in a straight up and down situation. Okay, so in the absence of other forces, the normal force is equal and opposite to the component of gravitational force that is perpendicular to the contact surface. So if we ever had to calculate a situation like this image over here, to calculate normal force, we simply take mass times gravity times the cosine of theta. That's that's your slight adjustment to that equation. Now, we said that gravity is a vector quantity, okay? And what that means is, what sign do we typically attribute to gravitational force? It's pointed downwards typically, negative. But when we're discussing normal force, it's the force that typically counteracts gravity, or at least acts in an upward direction. So the value, the magnitude of that acceleration is going to be the same, except it's going to be a positive 9.81. Okay? Because it's in the upward direction. It's important to recall that whenever we're calculating these. All right, so we've been talking about motion of objects and forces of objects and forces on objects. And some of those forces and inhibitors of motion is friction. Friction is a big player in our universe, I guess in our world. But without it, we couldn't do anything really. But with it, it can destroy. Give and take, okay? We're going to be discussing static and kinetic friction. Static friction is a force that resists the initiation of sliding motion between two surfaces that are in contact and at rest. So, currently, move this. It's always my favorite. Right now, there is static friction between the little feet on this podium and the tile floor. Okay, that's going to resist its movement. Okay, so in order to get something to move, you have to overcome that static friction. Then you have kinetic friction, which is the force that opposes the movement of two surfaces that are in contact and are sliding over each other. So, once I apply enough force to overcome that friction, there's now friction as I'm sliding this. There it is. There it is. So, kinetic friction will always be a lesser value or lesser magnitude than static. Okay? Because once you get something rolling or moving, it's typically easier to keep it moving. But in order to get something started to move, it takes a little more oomph. Has anybody ever had to push a car that was stalled out or whatever, or just wasn't operating? Okay. How much effort or force did it take you to get that thing moving? Quite a bit. But what I'm asking that is, compared to once you got it rolling, did it take quite as much to keep it rolling? No. Okay? Because we overcame that static friction between the tires and the ground and was able to use less force to keep it moving. When we talk about frictional forces, we can incorporate free body diagrams again. In those free body diagrams, the force of friction is always parallel to the surface of contact. Okay? And then the force of kinetic friction is always opposite the direction of motion. So, as I'm pushing the podium towards the back of the room, which direction is the kinetic friction acting on? Towards the front of the room. Okay? So to determine the direction of the force of static friction, we have to use the idea of equilibrium, which we mentioned 1 or 2 sections ago. So for an object that is in equilibrium, the frictional force must point in the direction that results in a net force of 0. So basically, anything that's going to be counteracting that in the same magnitude. Okay? Now, I have made the test for this chapter, since we're talking about free body diagrams. I have made the test, and it is Google Form Test. So again, there's not going to be any drawing on this one as well. Okay, you can draw as much as you want on your paper if it helps you with this, but you won't be doing any free body diagrams for the test. Okay. All right, so since we're talking about static and kinetic friction, we need to be able to calculate the static and kinetic friction. So this is what we call the coefficient of friction. And that is the quantity that expresses the dependence of frictional forces on the particular surfaces in contact. And that's our frictional, our coefficient of friction. We call that, and then we know what the name of that little letter is. Who? I heard someone say it. Sounds a cow make. Moo. Yeah. Moo. Okay, so 2 formulas here. To solve for mu k, which do you think that one is? Well, I guess it already says. It's the coefficient of kinetic friction. Where you take the kinetic friction and divide it by the normal force. For the coefficient of static friction, you have mu s. You take the static force, the max static force, and divide it by the normal force. You could say static friction. Now, these 2 calculations result in a value that does not have a unit. Okay? There are no units involved with coefficients of friction. So that's going to take a little weight off of you when you're calculating this. But again, like any other formulas, we can rearrange these to solve. So just taking a look here at some examples of coefficients of friction. For instance, steel on steel. Okay, if we had 2 steel objects resting on each other, it has a coefficient of static friction of 0.74 and a coefficient of kinetic friction of 0.57. So these are just giving you some examples of how we can compare static versus kinetic on various substances. Now you always want to check that when you calculate, or if you calculate for both, that your kinetic will be smaller than your static. If it is not, I think you got some problem. So you need to recheck your work. Okay? So let's take a look at a practice problem here, and then we'll do a couple other practice problems, then we'll be calling for a day. But before we do so, for your homework tonight, I need you to circle the following numbers. Ready? Number 1. Number 2. Number 3. Number 5. That's it. I am making sure they watch the video. Now I really want to. Actually, tomorrow's is going to be the last one anyway. So for this chapter. So anyway, we have a 24 kilogram crate initially at rest on a horizontal floor that requires a 75 Newton horizontal force to set it in motion. We are to find the coefficient of static friction between the crate and the floor. And I just need to get this. All right. So, what do we know? We know that we have a force that is being applied. You'll see it called this sometimes. We just saw it's called Fs max, but you also see it called, or the book might even call it force applied. Okay, it means the same thing. Okay, force applied is probably a better suit for this particular question because it says a force was basically applied to this crate. And so in this case, it was 75 newtons. Okay. Next thing we know that the mass is 24 kilograms. What we don't know is the coefficient of static friction. So since we know that that's what we have to solve for, we can use the formula that we just saw. Again, we don't know the normal force. Okay, it's not given to us, so we have to do a little calculation, but we can do it within the formula itself. And since we're not told that it's being applied at a certain angle, then it's just going to be your basic straight up calculation like we see here. You don't have to do any cosine or anything like that. So we get 75 newtons divided by 24 kilograms times 9.81 meters per second squared. What do we get for our coefficient of static friction? And there's no unit, so that's all you got to do. But I do want you to open up your books to practice D. I forgot to write down the page number. So it's going to be after practice C. And practice C was, page 139. I did write it down. It's just in a different location. Page 139. Let's look at number 3. Okay. Up here in front, again, I'm recording, so I'm not going to say your name. Could you read number 3 for us?
A museum curator moves artifacts into place on various different display surfaces. Use the values in table 2 to find Fs max and Fk for the following situations.
Okay. So, I think, did it even say the mass?
They do in like ABC.
Okay. Let's look at A. Okay.
A 145 kilogram aluminum sculpture across a horizontal steel platform.
Okay, so aluminum on steel has a mass of 145 kilograms. Okay, now we look at the table. Okay. Can anybody identify what the coefficient of static friction is between these two? 0.61. Okay. Does everyone see where that is before we, can you find it? Okay, I guess you can. Okay. What about coefficient of kinetic friction? Who else? Pink shirt.
We're on number
3. 3A.
There's a table to the left.
Oh, I was not.
Aluminum on steel.
Point UK, right?
UK, yep.
Yeah, the 0.47.
Very good. 0.47. And we know that to be 9.81 meters per second. All right. So we need to figure out what? The Fs max and the Fk?
Yeah.
Okay. So we're going to take those formulas and we're going to first let's solve for the Fs max. So basically that means it's going to be mu s times the normal force. So we know that the coefficient of static friction was 0.61. And we know that the normal force can be calculated by taking the mass of 145 kilograms multiplied by 9.81 meters per second squared. So what is our force that is being applied here? Back corner. Fire blanket. Fire blanket. You. What? 145, yep. That's the mass times 9.81 meters per second squared. Need a new marker. You get 1 second. You said you need 1 second. And since we're talking forces, is newtons. So that's the first answer to that. Next thing is we need to calculate the Fk. Okay? And so basically, that's going to look like that same formula just rearranged, mu k times normal force again. And so coefficient of kinetic was 0.47 multiplied by, again, 145 kilograms times 9.81 meters per second squared. Wrestling sweatshirt. Oh!
Well, I was off on that last problem, so just 668.5.
And this is also in newtons. So again, in your homework, if they do have it at an angle, just make sure you put the cosine of that angle in there. Okay. Questions on this? Okay. Well, you already have your homework. You know what problems to do. You got some time to work on them. If you get done, then you can turn it in before you leave. If not, just scan your work and submit it to when I upload this. I'm going to put all students' homework and video. You can just upload it directly into your name and the submission there, and that'll be it. Okay. I'm going to